The broadcast is now starting. All attendees are in listen-only mode.
Okay. All right. Good morning and good afternoon. My name is Grace. I'm with Rheology. Thank you everyone for attending our webinar. Today we have our customer at the University of Texas at Austin, Barton J. Deere. He is currently a PhD student at the University of Texas in Austin. And he is about 1 year to graduation. And today he will be talking about the viscosity and stability of highly concentrated monoclonal antibodies. And without further ado, I will go ahead and give the microphone to Bart.
Hello. Hi, everyone. Hi. Thank you for the introduction, Grace. Hello, everyone. I guess I'm assuming everyone can hear me and see my screen. So let me. Okay. So as Grace said, I'm Bart Deere, and I'll be presenting on a recent paper contrasting the influence of cationic amino acids on the viscosity and stability of a highly concentrated monoclonal antibody. Oh, hold on. Hi, Grace. Can you hear me now? Grace, can you hear me now? Okay, so, all right, so are the microphones working now? Can everyone hear?
Yes.
Okay, great, thank you. All right, well, sorry for that delay, but thank you again, Grace, for the introduction. And as she said, I am Bart Deere, and I work at the University of Texas at Austin, and I'll be presenting on a recent paper called Contrasting the Influence of Cationic Amino Acids on the Viscosity and Stability of a Highly Concentrated Monoclonal Antibody. So for this talk, I'm going to start by giving a brief overview of monoclonal antibodies, or what we like to call MABs, and their protein-protein interactions, or which we often refer to as PPI. From there, I'm going to talk about the addition of cosolids and how we can use those to tune these PPI, these interactions, to affect the antibody viscosities. And then finally, I'm going to relate those viscosities to the actual measurements of the interactions, and as well as to possible networks in the antibody solutions. Okay. So to start, antibodies are becoming a increasingly popular form of treatment in the pharmaceutical industry. One of the challenges, though, is that to be effective, they require very high doses. And to do this is typically delivered through a large volume solution through a slow intravenous delivery process. However, it would be much more efficient and therefore largely preferred if we could inject much smaller volumes but concentrated solutions of antibodies through subcutaneous delivery, which would be much faster and cheaper. However, the challenge with this is that as antibodies become highly concentrated, their viscosities become very high, as has been shown numerous times that the viscosity of antibody solutions increases exponentially with their concentration. Interestingly, even though all these antibodies have essentially the same size and shape, these viscosity profiles can be very different, as seen on this graph here. And so here I'm using 20 centipoise as kind of an average practical syringeability limit. That's variable depending on what you're going for. But as you can see, regardless of what you use as a syringeability limit, some of these antibody solutions max out above that cutoff at much lower concentrations than others. And one pertinent question is why? So we believe that the main cause of this variation in viscosities is the differences in interactions of these solutions. So as I said, as these proteins become concentrated, their spacing becomes much smaller, the separation between them. And this allows for short-ranged, particularly attractive interactions to affect the flow of these antibodies very much. So you have these attractive interactions come from a combination of electrostatic and hydrophobic forces. So the electrostatic comes from attraction of oppositely charged patches on the surface. As seen on this picture on the left, some of these antibodies have some negative and some positively charged regions. So when these come near each other, these opposite patches can align, causing a strong attraction. Similarly, hydrophobic surfaces can do the same thing. And this can cause the proteins to oligomerize or form networks, which can greatly restrict flow and therefore increase viscosity. Further work has shown that simulations of these, through coarse-grained simulations of these antibodies, where the antibodies that tend to have these more strongly attractive interactions and form more of these networks, as shown on the right, correlate with the antibodies that are very viscous at high concentration, while the antibodies that don't interact in this way are much less viscous. So one of our goals is to be able to tune these interactions. So you can take a highly attractive antibody that's very viscous and just add a small molecule co-solute to adjust these interactions to make the protein solution much less viscous. So in order to do this, you first need to understand the basics of these protein interactions. So on the left here, I'm showing a purely hypothetical, very oversimplified model of the potential interactions of proteins. So as you can see, at very short separation distances, within a particle, these are dominated by hard particle-like repulsion. However, as you get just away from the surface, so now that these surfaces are nearly in contact with each other, you have these short-ranged, very strong, attractive interactions which form this attractive well. But as you get further away from the surface, the strength of these attractions becomes much weaker. And now the proteins are able to diffuse and rotate freely. And since these are proteins all have the same sequence and therefore have the same net charge, when they're rotating freely, the main effect is seen as electrostatic repulsion. So therefore, these proteins have what's often referred to as a short-range attraction, long-range repulsion type potential. So if one were to add an ionic co-solute, just sodium chloride or any kind of salt, that will screen all electrostatic interactions. So it's going to weaken, it may weaken your attractive well by reducing the short-range electrostatic attraction shown here, but it will also weaken your long-range electrostatic repulsion, which can often have an ambiguous effect on the net interactions of protein solutions, and that's going to be important later on. Furthermore, if one were to take one of these ionic co-solutes and use one that can also screen hydrophobic residues, you would have the same effect on the long-range repulsion, but you would cause a further reduction of the attractive well. And so what we're going to do is compare these different kinds of systems and see how they affect viscosity and other properties. So one of the most effective and commonly used co-solutes for proteins is arginine, and particularly arginine paired with a hydrochloric acid, so arginine hydrochloride. And as shown for the antibody that we work with, referred to as MAB1, arginine caused a very large reduction in the viscosity. So as you see, it's going from over 100 centipoise at 225 mg per mil to about 25 with the addition of arginine. So it's over a 4x reduction. So now the lines on this graph are fits to the Ross-Minton equation shown here. Now, you don't need to worry about the details of what's in this equation. All you need to know is that the Ross-Minton equation is a hard particle semi-spherical viscosity model. So it doesn't account for any kind of attractive or repulsive forces outside of hard particles just bumping into each other. And those particles need to be vaguely but not exactly spherical. So on the right, what I'm showing is a linearization of this equation. So when you plot the data this way, any data that truly follows the model should be linear. And as you can see, the arginine solution follows the model very well. It's nearly perfectly linear, falling exactly in line with what the model is predicting. However, the system with no cosolute has this sort of kink. It doesn't follow this linear behavior. And that indicates that this solution is affected by other interactions that are not incorporated in the model, such as attractions or repulsions, where the arginine is screening these out. So next we decided to compare a series of cosolutes to figure out what specifically about the arginine was causing these reduction interactions and viscosity. So again, here I'm showing more details than necessary, but really if you just focus on these few in different colors on the right, so green is indicating that this cosolute will affect ionic strength, and the yellow or orange is saying it's not going to affect it as much because the cosolute isn't quite fully charged, and red means it doesn't. So in this case, sodium chloride will screen the ionic strength, but it won't form hydrogen bonds with the protein. It won't screen any aromatic residues, or doesn't have a zwitterion attached. But what's really important, we believe, is this column on the right, the screening of aromatic regions. So proteins have various aromatic residues on their surface which can form hydrophobic interactions with each other. Now these cosolutes, with the green marked in this column, arginine, histidine, and imidazole, have been shown to favorably interact with aromatic residues, and therefore these molecules could interact with aromatics on the protein surface and therefore screen these hydrophobic interactions, which we think could further reduce the attractive well as shown earlier. So when we compare the effects of these different cosolutes on MAB1, you can see that the cosolutes that don't screen the aromatics, the sodium chloride and the lysine, they have a very weak effect on the viscosity of MAB1. We're adding 250 millimolar of these cosolutes. This 250 millimolar should extend to the sodium chloride as well. That's also the same concentration. But you can see they all have a very weak effect on the viscosity. However, when you look at these cosolutes that screen the aromatics as well as the electrostatics, now you see this large viscosity reduction for all three of these cosolutes. So that indicates to us that this screening of hydrophobics is very important for MAB1 in particular. So okay, now that we've established what we think is happening, we want to actually see what physically, screening these interactions, how is this physically changing the solution to reduce the viscosities? So our theory was on MAB oligomers and networks. And so we believe that if you have a networked solution, something that looks like this, where the proteins are all interacting with each other, if you shear the solution hard enough, you can add enough force to break these networks apart back into a free monomer solution. This would result in a shear thinning behavior, as the networked solution at low forces, low shear rates, is going to be very highly viscous because it's in a network. But once you break those networks apart, the viscosity will go down. And this has been seen for several protein solutions as shown here. Furthermore, we're going to model this behavior with what's known as a Corot model, shown here on the right. Again, you don't need to worry too much about the details, but mostly about this N parameter, which I'm showing for this data from literature. And as you can see, as the N becomes closer to 1, the data becomes less shear thinning and more Newtonian. So in our case, what we believe is less networked, while the more shear thinning ones with higher networks are going to have lower N values. So we used our RheoSense MV-Rock to measure the solution, the viscosities of a few of our solutions. So here we're showing the same MAB1 with no cosolute at 220 mg per mil, and then the MAB1 with 250 millimolar arginine at 230 mg per mil. Now, as you can see, in addition to this large reduction in viscosity from the additional arginine, even though it's at higher concentration, you also see this reduction in shear thinning, where the no cosolute one shows the shear thinning behavior. However, unfortunately, we weren't able to get data in this region in the high shear rates for the highly viscous system because the pressures became too high on our instrument. So we diluted the no cosolute system to 200 mg per mil to see if we still saw the shear thinning behavior, which we did, as shown by this curve right here. Furthermore, we want to look at other co-solids. Oh, okay, before I get to that, as you can see, the N values support what you can see visibly with the shear thinning, in that the highest concentrated solution with no co-solid has the most shear thinning. As you lower the concentration, you're reducing some of the networks, and the arginine reduces the networks a lot. Okay, so additionally, we wanted to look at the sodium chloride to see, that solution didn't reduce the viscosity very much, so did it have an effect on the shear thinning? Now here it might look like the sodium chloride reduced the viscosity, but keep in mind that's because this sodium chloride is only at 190 mg per mil, while these no co-solids are at 220 and 200 mg per mil. So I'm going to and also keep in mind all of this data is at pH 6. So another way to tune interactions other than addition of co-solids is by adjusting the pH, and this can change the charge on the proteins. So in our case for MAB1, lowering the pH made the protein more repulsive and less viscous, as shown by this orange curve, which is at pH 5. Now I'm going to zoom in on this region in this black box just to see this data a little more clearly so we can talk about it. So here, now I've just zoomed in on that region for these four systems. If we focus on this the pH 5 data, and the sodium chloride data in the green. As you can see, these are almost identical viscosities at low shear rates. So typically the same viscosity. But the pH 5 solution is at 230 mg per mil, where the sodium chloride one is only at 190. This was done intentionally so that the 230 mg per mil solution, being much more concentrated, you would expect to be more viscous, except that it's a less networked solution. So that being at the lower pH, the protein hasn't formed these oligomers or networks, and for the given concentration, it's much less viscous than the sodium chloride one. And as you see, when you increase the shear rate on this pH 5 solution, it only very weakly reduces the viscosity. And that's because there aren't very many networks to break in this low pH solution, because not many have been formed. While the sodium chloride one, which has the same low shear viscosity, but it has this viscosity, viscosity is largely affected by these networks. Those can be sheared out, and that viscosity drops as the shear rate is increased. So after looking at those oligomers, we wanted to measure directly the interactions. So we went to a relatively common technique used for measuring protein interactions. It's using dynamic light scattering to measure the diffusion interaction parameter, also referred to as the KD. Now on the left here, I'm showing just a reminder of the effects of these co-solids on the viscosity. So no co-solid is quite viscous, adding sodium chloride only weakly reduce that, while arginine causes large reduction in viscosity. However, when we look at the measured interactions, you see what might seem as a somewhat surprising result, whereas if lower KDs mean more attractive interactions. So as we add arginine, we're actually seeing the system looks more attractive by this KD measurement than no co-solid. Now the sodium chloride is even more attractive. Now to understand what's going on here, we need to think back to what we remember at the beginning when we were talking about these interaction potentials. So as we mentioned earlier, when you go from no co-solid to adding any kind of ionic co-solid, you can screen the attractive well, but you're also going to screen the long-range electrostatic repulsion. Now, these DLS KD measurements are done at dilute conditions, so the average protein separation is large, very large compared to the viscosity measurements we were looking at earlier. And because of that, the main interaction between these proteins is this repulsion. So adding any of these ionic co-solids are kind of obviously going to reduce the KD and make the system seem more attractive, because you've lost this large repulsion. Now, when we compare the two systems, the arginine and the sodium chloride, which have the same screening effect, so have reduced the repulsion the same amount, now you can see the arginine is much less attractive, indicating that it reduced the attractive well. It screened the attractive interactions. So to kind of get a better understanding for this, to see if we could use these KDs to predict viscosities for systems of varying ionic strength, we created this kind of very oversimplified model where we said that we've made a predicted viscosity based off of two parameters, the measured KD and then the Debye length of the solvent that the protein is dissolved in. So that's going to be directly calculatable from the ionic strength, which can depend on the concentrations of the co-solutes and how charged they are. And as you can see here, for a measured, and the idea of this is that if you have the same measured KD for two systems of varying ionic strengths, the one with the shorter Debye length is going to have more repulsion screened out of it. So it's going to have, so the same measured KD with a system that has less repulsion must also be less attracted. And we think that's what's going to have the main effect on the viscosity. And as you can see, if you move left for a given KD on this curve, you get to lower viscosities. And that's what our data suggests from this interpolation here. Furthermore, we compared this with some data from literature. So these red points are our data from MAB1, where these blue are our data we found from this Connolly paper. It's Connolly 2012, I think Biophysical Journal paper. And we showed that there's this pretty good general correlation where this model can sort of predict the viscosity at high concentration, regardless of the ionic strength of the solution. So in conclusion, we're able to use co-solutes to successfully screen the short-range attractive interactions to reduce the viscosities for the MAB we were studying. And through a combination of dynamic light scattering and shear-dependent rheology, we believe that these reductions in viscosity are due to the screening of interactions, which are causing a reduction in protein oligomerization and network formation. And so with that, I would like to answer any questions anyone may have.
All right, so if you have any questions on the right side of your navigation, there should be a section for questions. And Bart will select a few and go ahead and answer. Bart, just give me about 2 seconds.
Okay. Okay, so the first question I see here is when I describe networks, whether or not I believe the antibodies are percolated like a gel or merely clustered with the clusters remaining in free suspension. And I definitely do not believe these are percolated like a gel. I believe it is possible that in some solutions you could get to that, but these viscosities are much too low to be a percolated gel. I believe these, when I refer to networks, I'm more referring to, as you said, protein clusters or small oligomers that may be entangled or something. But I do not believe this is a percolated gel. Okay, the second question on here says, are there any changes in the diffusivity or hydrodynamic radius of the proteins in addition to the changes in KD with the addition of sodium chloride or arginine? That's a good question. Definitely you'll see differences in the diffusivity, the diffusion at infinite dilution, but this is mostly due to the difference in solvent viscosity. So when you account for that and look at the hydrodynamic radius of these dilute solutions, they're very, very similar. I don't believe they were exactly the same, and I don't remember which one was higher or lower, but they were both within 9 to 10 nanometers, if I recall. The third question is asking whether or not we can apply this idea to peptide formulations. And the very short answer is I do not know. I have not done any work with peptide solutions, so I'm not sure. However, I can conjecture that if the peptide solutions are seeing, if these same interactions are causing whatever challenges, whether it be aggregation or viscosity in your peptide formulations, I believe it likely could work and would definitely be worth trying, but I don't know for sure. Okay, next person would like for me to elaborate on the KD measurement and how we go about that. So we got our procedure for measuring KDs in this paper directly from the Connolly paper I referenced, which it looks like I may have forgot to put the reference on the slide, so I apologize for that. But basically what we did is we measured the diffusion coefficient using dynamic light scattering at, I believe it was 2 instead of 1. So we used 2, 5, 10, 15, and 20 mg per mil. Measured the diffusion coefficient of these solutions at each of those concentrations, and then we fit a linear line to the data. And so the y-intercept of that line will be your D0, your diffusion coefficient at infinite dilution, and then the slope will be the product of the D0 and the KD. So we just divided that slope by the y-intercept to get the KD, and that's how we measured those. And no, we did not use a Rheology coefficient for this map. Yeah. Okay, so I believe this is the final question we have time for, and they asked me if I've seen phase separation in these solutions at high concentration, and if so, how I go about measuring the viscosity of these, and if I have a good way of dealing with this. So I have not seen phase separation in any of these solutions I've measured the viscosities for. I have seen it in some solutions, but only for long time storage, where I've taken one of our more viscous solutions and stored it and then seen it phase separate over time. But I have not tried to measure the viscosity of the phase separated solution. I'm not, in terms of practicality, I think that if the solution is phase separating, you wouldn't be able to inject it into a person anyway. So I don't know if that viscosity really matters for practice. If you want it for something else, I guess my recommendation would be to measure each phase separately, but it depends on your application. Okay, actually, looks like we are going to have a few more questions. So let's see here. The next question is, asking if I've examined changes in the suspension structure with arginine via a technique like neutron scattering, and are the interactions just weaker? Is the cluster distribution changing? So I have not used neutron scattering, but what I have done is used X-ray scattering, which is very similar. And we are actually currently working on that. And I will just say, I guess I don't want to give too much away of what we're doing, but yes, I think we've seen some very interesting differences in these solutions, and we're relating that to cluster distributions at high concentration. And so none of that's not ready yet, but I think we are seeing some of this, and hopefully you can see some of this in a future publication. The next question is asking how I measure the concentration of the solutions. And so what we do is we use the UV vis to measure the A280s at 280 nanometers. Obviously you can't do that for a extremely high concentrated solution, so we have to make a dilution. So what we do is we make several dilutions of the sample and measure the concentration of those directly using UV vis, and then back calculate what the concentration must have been. We also know from mass balances through our filtration processes that we know that we're about in the right range. So that's how we've gone about measuring the concentrations. Okay, and the final question is the minimum protein concentration to do this. I guess I'm not entirely sure what you mean by this. In terms of viscosity measurements, you could measure it as low as you want. For the KD measurements, we use a series of concentrations all the way down to 2 mg per mil. You could technically go lower, but in our case, we don't, because our dynamic light scattering unit doesn't get a significant signal from these proteins at less than 2 mg per mil, so you don't really get a measurement. But as long as you get a significant measurement, enough scattered light intensity, you could do that measurement as low as you want. So for the shear dependent rheology, again, you could do it for a buffer as low concentration as you want, as long as the rheometer you're using is accurate in the viscosity range you're looking at. Okay, so I think that's the final questions. I think I'll hand this back over to Grace. So thank you everyone for listening and for asking such interesting and insightful questions. Thank you.
Thank you, Bart. So any questions that we weren't able to answer will be answered separately through an email. Many of you had asked if we would have the slides ready and available. We will have a copy of the webinar ready probably by no later than the end of Friday. And you will receive a notification from our team when the recording is ready. So please feel free to contact us if you have any questions, and thank you everyone for attending today. Thank you, Bart.
You're welcome. Thank you. Bye.